DSDC Airport Technology Report describes DSDC's GPS research, including demonstrations for the U.S. Federal Aviation Administration and DSDC's patented airport control and management system. The concepts and techniques demonstrated at Manchester, New Hampshire Airport will provide the pilot and air traffic controller with a seamless airport environment. A precise ground survey was conducted in preparation for GPS-based aerial photogrammetry. System accuracies were verified using precise monumentation markers located in accessible areas. Aerial photogrammetry was collected using a Wild RC-20 camera. A 3D map database was constructed using a Zeiss 3D digitizing table. Map details were generated with an absolute WGS-84 accuracy of better than 1 meter. Early flight tests were conducted using the services of Daniel Webster College of Nashua, New Hampshire. A Mooney 201 was equipped with GPS equipment and a laptop computer. Flight and taxi data was collected and merged with a 3D digital airport map. A U.S. patent was awarded on April 6, 1993 to H.R. Pilley for work involving the application of GPS and highly accurate digital maps for airport control and management. Manchester Airport was the site of a GPS-based airport service navigation test. An FAA Convair 580 arrived with representatives from the FAA Technical Center and Satellite Program Office. As the Convair taxied on the airport surface, its position was clearly plotted in the onboard moving map display. A VHF data link was used to send the aircraft's position to a simulated ATC display. Verification of the position was performed using the precise monumentation and from within the aircraft. The demonstration was a success. Under a Phase 1 SBIR contract, DSDC performed enhanced differential GPS precision landings using a GA aircraft. The GPS landing system was designed to fly the same glide slope as the ILS. The performance of the GPS system was as good as, if not better than, the ILS. DSDC demonstrated its airport control and management system to federal, state, and local officials. Mike Harrison of FAA headquarters attended the demonstration. DSDC hardware, software, data links, and differential GPS equipment was installed in surface vehicles for ground navigation and vehicle tracking. A color flat panel LCD display was used to show situational awareness, zone incursion, and collision conditions. Similar equipment was installed in the Mooney test aircraft. Real-time collision detection was performed. Various collision scenarios were demonstrated, such as head-on and overtaking situations. Collision alerts were generated aboard vehicles and at the AC&M station. Differential GPS landings were conducted. Digital waypoints and clearances were issued to the aircraft. Throughout the tests, the vehicles were monitored at the AC&M station. A user command interface was provided by a touch screen. The display view command is used to control the display presentation. Upon selection of this command, a list of standard views is presented in the blue message composition window. When the 1 mile option is selected, the airport map is redrawn and scaled to a 1 mile plan view presentation. The graphical display provides the current position of monitored vehicles in the airport map. In this view, the Mooney aircraft is landing on runway 35. The vehicle position is represented by a scaled symbol with numeric and color identifiers. As the aircraft lands and taxis, the display can be zoomed up to provide a more detailed view of its current position. Other display views may be selected at any time using the page up and page down touch keys. Three-dimensional and side views may be selected for any runway. Upon selection of the runway 35 3D option, the airport map is redrawn to depict an elevated view from the south. Here we see the Mooney aircraft approximately 7 miles out as it begins its final approach to runway 35. The concentric range rings represent 1-mile increments from the center of the airport. 3D airport map presentations may be used at the AC&M to monitor arriving and departing aircraft. Aboard the aircraft, 3D map presentations may be used for situational awareness and as a navigational aid. A side view display can be selected to show the aircraft's vertical descent profile. Simultaneous display of the waypoint travel path can also be displayed to provide information as to the current on or off course conditions. Arrival waypoints and clearances are generated using the Arrival Waypoints touch key. A list of valid vehicle tags is displayed in the Vehicle List window. The aircraft's identification tag is selected and a list of standard arrival waypoint paths is displayed in the Message Composition window. Each waypoint list is represented by a textual description of the travel path. Here the waypoint path representing a landing on runway 35 is selected from the list of valid trajectories. The waypoint path is then drawn into the situation display at the AC&M station. As the aircraft approaches the runway, its position may be monitored with respect to the waypoint trajectory. Various display perspectives may be invoked using the touchscreen Display View command to monitor the aircraft's approach. After the waypoint path is displayed in the digital map, the operator is prompted to verify the selection. If the selection is accepted, the waypoint message is transmitted to the aircraft over the data link. During its final approach, the aircraft's position, heading, and velocity are continuously monitored at the AC&M station with respect to the issued waypoints. Again, various display views may be invoked by the AC&M operator. In this demonstration scenario, the issuance of arrival waypoints automatically results in a clearance for the selected runway. Because the aircraft is cleared for an approach on runway 35, no runway incursion condition is detected as the aircraft approaches the runway. As the aircraft lands and begins its taxi, DSDC's concept of a seamless airport environment is clearly demonstrated. The same equipment, installed on aircraft and in surface vehicles, can be used to provide tower controllers with a view of all air and ground movement within the terminal area. Departure waypoints and clearances are generated using the Departure Waypoints touch key. The desired vehicle is selected, followed by the waypoint path. The waypoint path is displayed and reviewed in a fashion similar to the Arrival Waypoints function. Upon command review and acceptance, the waypoint and clearance information is sent to the selected vehicle over the data link. On board the aircraft, the travel path and waypoints are drawn into the map display. At this time, a valid clearance has been issued, and the pilot may start his taxi. As the vehicle moves, its position with respect to the digital map is precisely displayed. No ambiguity in the aircraft's position was observed when compared with the outside landscape. For surface navigation, the pilot found the monochrome LCD map display with travel path information very useful. With this type of map navigation display, the pilot will never be lost in the sea of blue lights again. Upon reaching the takeoff runway, the DSDC navigator is used for the departure guidance. The navigator provides an auto-indexing color-coded waypoint range legend, waypoint range rings, current course and bearing displayed in a compass rose presentation. Course and bearing arrow lengths represents waypoint distance. Altitude information is displayed as a bar graph. The crosshair display provides turn left or right and go up or down information. The Mooney test aircraft departs the Manchester Airport using the DSDC navigator, with course information provided by the AC&M station. Vehicle data may be displayed for any active vehicle using the Vehicle Data touch key. The displayed data includes the vehicle's identifier, type, collision radius, current heading, speed, range to the waypoint, cross-track error, course status, clearance status, and current waypoint. Previously issued clearances and waypoints may be canceled on an individual vehicle basis by the AC&M controller using the Clear Path Waypoints touch key. The Layer Filter touch key may be used to display and suppress various map layers. The status of all suppressible map layers is displayed in the message composition window. Here, the Airport Surface Zones layer is enabled, resulting in the display of surface areas with restricted usage. These surface zones are keyed to vehicle type. If a vehicle enters a zone which is restricted to him, a zone incursion alert is generated. Airport lights may be manually enabled and disabled through the Airport Lights touch key, or may switch automatically based on vehicle position and clearance status. When the runway 35 landing lights are enabled, the lights shown in the lower right corner of the airport lighting model turn green, and the runway intersection lights turn red. The 3-foot by 4-foot airport lighting model is used to represent various runway lighting configurations. Similarly, when the runway 35 landing lights are disabled, the lights in the lower right corner of the airport lighting model turn red, and the runway's intersection lights are turned off. Collision conditions are detected at the AC&M station and on board the vehicles. As the vehicles approach each other, a collision watch condition is detected. As the collision becomes imminent, a collision warning condition is detected. 4D collision detection is provided by DSTC's patented and patent-pending techniques. As the vehicles pass, the collision condition is canceled and the vehicles revert to their normal operating conditions. The collision condition is shown graphically at the AC&M station. The yellow vehicle symbols represent a watch condition, and the red symbols represent a warning condition. The symbols return to their default colors when the vehicles pass each other and the collision condition is canceled. This real-time display presentation may also be provided on board the vehicles. Clearance and zone processing is a key element in DSDC's airport control and management system. Here the digital map is shown with the restricted airport surface and runway zone layers enabled. Zone and clearance processing is carried out in the Earth-centered, Earth-fixed Cartesian coordinate frame. The highlighted area identifies a surface vehicle which is about to move into a restricted area. The vehicle symbol changes to red when the vehicle crosses over the boundary line into the forbidden zone. As the vehicle moves within the zone, its color remains red. When the vehicle travels out of the zone, the symbol returns to the vehicle's default color. The vehicle now approaches runway 624 without a valid access clearance. The vehicle symbol turns yellow when a zone incursion watch condition is detected. The symbol turns red when the vehicle position is within the runway zone. The symbol remains red, and the alert condition is generated in the AC&M alert window. As the vehicle approaches runway 1735, another runway incursion watch condition is detected, and the vehicle symbol is displayed in yellow. An alert message is displayed in the AC&M alert window. As the vehicle moves into the intersection of the two runways, the vehicle symbol changes to red. As the vehicle leaves runway 1735, the vehicle symbol remains red, since it is still incurring runway 624. As the vehicle departs runway 624, the incursion condition is cleared. The symbol turns yellow briefly as it approaches a grass divider, but returns to its default color when no zones are being incurred. An incursion on runway 624 results in the flashing of the runway's lights. Both sets of runway lights flash when an incursion occurs at the intersection of the two runways. Upon exiting the runway, the respective warning lights are turned off. DSDC's AC&M clearance and zone processing automatically controls the simulated airport lighting system using GPS-based ADS position reports. The patented system of DSDC will provide the pilot, vehicle operator, and air traffic controller with a 4-dimensional airport control and management capability. DGPS and ADS can be used to provide situational awareness, collision prediction, precise navigation in the air and on the ground in all weather conditions. The accuracy, cost-effectiveness, and overall simplicity of the DSDC system will make it deployable at large and small airports. The concepts presented here will make airport and aviation operations more cost-effective and safer, regardless of your final destination.